Welcome to the TOEFL Listening section. In this section, you will listen to an academic lecture and then answer questions about what you heard. You may take notes while you listen. You will have time to review your notes before answering the questions. Listen to part of a lecture in a university class. You will hear the lecture only once, so listen carefully. After the lecture, you will answer some questions about what you heard. Some questions ask about the main ideas and supporting details. Other questions ask you to make inferences or connections between ideas. Answer each question based on what is stated or implied in the lecture.
Today we will examine the formation of solar systems, starting from a collapsing stellar nebula and ending with a system of planets and smaller bodies. The process begins in a cold molecular cloud, where a region becomes gravitationally unstable and collapses, conserving angular momentum and forming a flattened protoplanetary disk around a central protostar. Within that disk, microscopic dust grains collide and stick together through electrostatic forces and then grow into millimeter and centimeter-sized pebbles. These pebbles are critical because they can be concentrated by gas motions and streaming instabilities to form kilometer-sized planetesimals relatively quickly. We call these bodies planetesimals, and they are the building blocks of planets. Once planetesimals exist, growth proceeds by collisions and by a process called pebble accretion, where larger bodies more efficiently capture small solids, accelerating core growth. One classic model is core accretion, in which a rocky or icy core reaches about 10 Earth masses and then binds a massive envelope of gas to become a gas giant. An alternative pathway is disk instability, where regions of the disk rapidly collapse under their own gravity to form gaseous protoplanets without a prior solid core. Which mechanism dominates depends on local disk mass, temperature, and cooling rates, and both mechanisms may operate in different systems or even in different parts of the same disk. A key concept is the snow line, the distance from the star, where temperatures are low enough for volatile compounds like water to freeze as ice. The location of the snow line determines where ices can condense, and this affects whether planets become gas giants or remain rocky. I want you to remember that outside the snow line, solid material is more abundant because ices add mass, so cores grow faster and can more easily accrete gas. Observations give us concrete examples that inform these theories. For instance, ALMA images of the young star HL Tau reveal rings and gaps in the protoplanetary disk that likely indicate early planet formation. Meteorites and chondrules in our own solar system provide isotopic and chronological evidence that planetesimals formed within the first few million years of the solar nebula. Timescales matter because the gaseous disk dissipates in a few million years, so gas giant cores must form before the gas is lost. Migration is another crucial process, where interactions between forming planets and the disk cause planets to move inward or outward from their birthplaces. Migration explains why we see hot Jupiters, gas giants very close to their stars, which could not have formed in situ inside the snow line. Resonances and orbital dynamics during late stages can sculpt a system, clearing gaps, exciting eccentricities, and delivering water-rich bodies to inner rocky planets. When we compare the solar system to exoplanet systems, we see a diversity of outcomes, but common physics underlies all of them, namely disk evolution, accretion processes, and migration. To summarize, formation of a solar system proceeds from molecular cloud collapse to disk formation, dust coagulation, planetesimal formation, core growth by collisions and pebble accretion, and finally planet assembly influenced by migration and disk dissipation. By combining observations like ALMA images and meteoritic data with theoretical models, we can reconstruct plausible timelines for how diverse planetary architectures arise.
Listen again to part of the lecture, then answer the question.
The location of the snow line determines where ices can condense, and this affects whether planets become gas giants or remain rocky.
This concludes the listening section. For more TOEFL practice tests and study materials, visit Spinta.org.